All right, is that working? All right, is that working?
Are you back up and going?
All right, is it still whooping, Miles? I had to turn the volume down. All right, good. Sorry about that. I'm just getting some of the kinks worked out. I haven't done this too many times. So we'll start again. Thanks for joining me. Like I said, the review sheet's in the description, so if you guys want to look at that, tell me what number you want to start with. If not, I can just talk about random things, but it's best if you let me know what problem you want to talk about. Alright, well, if you guys have no questions, I'm going to have to talk about something. Otherwise, I'm going to stand up here and doing nothing. So, I'm just going to start off with number... Oh, thank you, Aaron. I would appreciate that. So, number 9, sure. So, for number 9, we want to use the limit definition of derivative to find the derivative of square root of x. So, let's find f prime of x if f of x is the square root of x. So now where I want to start off with this one is we have to remember what is the limit definition of derivative. So before we can go anywhere, we need that. And so the limit definition is, well, the derivative of a function is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. And so Caitlin and Lila, thank you. We'll get to those next. If you guys have any questions along this one along the way, let me know so I can stop and do them. But so here we are. We have the limit definition of derivative, and if we want to find that, remember that we did this in 4 parts. We started off with f of x plus h, and then we subtracted f of x, we divided by h, and then we took the limit as h goes to 0. So for this one, we would just say, okay, well, f of x plus h is the square root of x plus h. Now, can I simplify that at all? Well, no, I can't. So I have to continue on, and the next step would be find f of x plus h minus f of x, which is going to be the square root of x plus h minus the square root of x. And so again, the point here is we want to know, can we simplify this? And now, it doesn't look like we can do much here, but we know that we're going to have a limit. And in the end, if we look back at this limit, we're going to end up with f of x minus f of x over h over 0 if we plug in 0. So we get 0 over 0. So we're going to have to do some canceling. So what we want to do here is something to simplify this so that eventually we can do some canceling. So maybe you guys can help me out here. What should I do here? Complicated. That is correct. I think it was complify it. So I wanted to complify, or make it more complicated in order to simplify it. And the way I'm going to do that is multiply by the conjugate in this case. Very good. Thank you. And so if I multiply by the conjugate, remember I'm going to turn this minus into a plus. And so to have some more room, I'm going to erase some of this. And I want to take the square root of x plus h minus the square root of x. And I'm going to multiply by the square root of x plus h plus the square root of x. And then I'm going to divide by that so that I don't change the problem. And now when I multiply, remember this times this, the square root times the square root cancels, and we get x plus h. And then we get square root of x times the square root of x plus h, but then minus the square root of x times the square root of x plus h. So those cancel, and then we get negative square root of x times positive square root of x is just negative x, all over the square root of x plus h plus the square root of x, which is left over from when we had to keep it the same. So now notice this simplifies some more. So we can get rid of the x's because we have an x and a minus x. And so we have just h over the square root of x plus h plus the square root of x. So we're going to continue with our simplification. And the third step is to take that and divide by h. So I'm going to take step 3, f of x plus h minus f of x all over h. It is h over the square root of x plus h plus the square root of x. And then to divide by h, I'm just going to multiply by 1 over h. So now at this point, remember that the h's cancel as long as h is not 0. So we get 1 over the square root of x plus h plus the square root of x as long as h is not 0. So now the whole point of that is that we went through and we actually simplified the inside, but remember we wanted to find the limit if we want to find the derivative. So what we found was that this was equal to this, and since we're taking the limit, we don't have to worry about h being 0. So what we get in the beginning here is, the derivative is going to be the limit as h goes to 0 of, well, what we have left over here is 1 over the square root of x plus h plus the square root of x. And so now what we've done is we've taken a complicated limit and turned it into an easier limit. And so now in order to calculate this limit, the first thing we want to do is plug in h equals 0. So if I plug in h equals 0, I get 1 over the square root of x plus the square root of x because the h is 0. Notice that there's no more h's in here. X acts like a number because it doesn't change with respect to x. So this is a number. So what we get is 1 over, and if we add those together, we get 2 square roots of x. So that means that this limit has been calculated. It's just this, which means that the derivative of square root of x is 1 over 2 square roots of x. So now remember that on the test, you're going to have to show that work along the way. I want to actually see f of x plus h minus f of x all over h, and then simplify along the way so that you can find this limit, because that's the whole point of this problem. Does that make sense? Do you guys want to go over another one? Or is that good enough? Okay. The other one I would suggest, if you're okay with it, that's good. But the other one I would suggest trying is going through 1 over x. Because that was the one I suggested in class to go over. So if you would like some little extra practice, go through and find the derivative of 1 over x by using f of x plus h minus f of x over h. I'll leave that one for now. And I'll go on to the next one I see, which is the optimization. So let's go to the optimization problem. Which I believe was number 20. So we'll go ahead and do number 20. If you guys have the test in front of you, I'm not going to write the whole thing down because it's kind of long, but you can follow along as we do that. What we have is, I recently decided I wanted to make a garden in my backyard. And, well, I don't have a huge backyard. I should have enough room to make a small garden. I have 24 feet of usable fencing that I can use to enclose my garden. So I already have fence around my backyard, so I can use that fence for one side of the rectangular garden. And then I want to know what dimensions should I make my garden in order to maximize the total area of my garden. Alright, so help me out here, guys. I have something going on in my backyard. I'm going to make a garden, so I should start off, I read it. The next thing I should do is draw a picture. What should my picture look like? Well, let's see. I already have my existing fencing. I want to draw the whole thing, or even a shed back here somewhere. And so the idea is that I'm going to now draw in my new garden. So there's going to be fencing. I want to make it rectangular, and I want to use my existing fencing as one of the sides. So I end up with very good Killerman, a box. So I get a box here. This is my garden. And the point is I want to make the area as large as possible based on the fact that I have 24 feet of fencing. So now that I have my drawing, I want to write in anything I know. And the only thing I really know is that I have 24 feet of fencing. And I want to maximize the area. Alright, so now that I have that, I want to decide what's variable in this situation. So what's variable, or what I have control over, is I get to decide the dimensions of this rectangle. So that is, the dimensions of the rectangle are determined by its width and height. So I'm going to call this the width and this the height, because that's what it looks like on my picture. So I'm going to use W for width and H for height. And now those are my variables because those are the things I can change. I can decide how wide or how high to make it, but I can't really decide anything else because everything else is given to me in the problem. Now that I have my variables, what I want to do is, well, I know I want to maximize the area, so I have to find an area function. So because I have a rectangle here, notice that my area is just going to be height times width. Now, the problem with this function is, remember, we're trying to optimize it, but we have two variables, right? So we don't know how to deal with two variables at a time, so what we need to do is change this in the function of one variable by using something that's given to us in the problem. So what is given to us in the problem? All right, guys, help me out here. What's given to us? All right, very good. We have 24 feet of fencing. So how do we use that is, notice that there's fence here, there's fence here, and there's fence here. Notice this side we don't have new fencing in because we have existing fencing. So we get, well, we have 1 H of fencing and 2 W's of fencing. So we get 2W plus H is equal to 24. Now with that, we can solve for one of the variables in terms of the other. So I'm going to solve for H by subtracting 2W, and I get H is 24 minus 2W. Now, what we get is, okay, well, H is 24 minus 2W, so I can put the area together is now going to be H is 24 minus 2W times W. So H times W. And so now I have a function in terms of one variable that I need to optimize. So we can do that as long as we can find an appropriate domain. And so here what we're going to say is, what is the smallest W can be? What is the smallest H can be? And so if we look at that, well, since this is a length, the smallest W can be is 0. And now, so we know 0, or W is bigger than 0. I'm going to say it can be equal to 0. As a picture that would just look like this. Would be kind of boring. If you don't like that, you don't have to. You can say 0 is strictly less than W. But the reason why I'm picking this is because then I end up with a closed bounded interval, so it makes it a little easier to find the optimal answer. Now, on the other hand, since H has to be bigger than 0, if H is equal to 0, what I get is a picture that looks like this. Now, if we have a picture that looks like that, remember that we have still 2 W's. So now I would just ask, what is the biggest W can be? So if I have 24 feet of fencing, I could go out 12 and back 12. So the biggest W can be is 12. So now we have a restricted domain so that our area is this, and it's on a closed bounded interval. So we'll notice that we have a continuous function on a closed bounded interval. So we have to have a max, and we have to have a min. And where does the maximum and minimum have to occur? So help me out, guys. Where do those occur? right, critical points. Glad you guys are answering my questions. There's a little bit of delay, so I'm staying up here doing nothing for a little bit anyway. So if you don't answer, I don't know what I'm going to do. All right. Anyway, though, going back to this, they occur at the critical points. So what I need is to find those critical points. So I'm going to have to find the derivative. And so to find the derivative, I'm actually going to simplify this first. I get 24w minus 2w squared. So the derivative, a prime, is going to be 24 minus 4w. So now we need to know where that's 0 and undefined. Now, if I just look at 24 minus 4w, that's a linear function, so that's going to be defined everywhere. But when we say undefined, we mean undefined in the context of the problem. So within the context of the problem, we decided that w is between 0 and 12. So remember, at the endpoints, my derivative is undefined. So what I get is that a prime is undefined if w is 0 or 12. So we're going to have two critical points right away at w equals 0 and w equals 12. The next point we would have is, where is my derivative equal to 0? Well, my derivative is 24 minus 4w is 0. So if I add over, I get 24 is 4w. So w is 6. And now if I look at 6, notice that 6 is between 0 and 12. So it is indeed in the domain. So it is a critical value. So I know that this function has a max, and it has a min, and it has to occur at the critical values. So how do I determine which one gives me my maximum? I'll let you guys answer that one. All right, plug into the equation. That's exactly right. So we're just going to make a table. We have w, and now we're going to plug into the area function. So we have 0, 6, and 12, or my critical values. So if I plug those into the original area, if I plug in w equals 0, I get 24 times 0 minus 2 times 0 is 0. If I plug 6 in, I'm going to use this one. I get 24 minus 12 is 12 times 6 is just 72. And then if I plug in 12, I get 24 minus 24 is 0 times 12 is 0. And so what we get is, well, the smallest area would be 0, and that would be if we had no width or no height. So that actually makes sense, but it's not what we're looking for. What we would get is the maximum area would be 72 when w is 6. So now we've solved our problem. We know that w has to be 6 to get a maximum area of 72. So now we just need to go back and make sure to answer the original question, which was, what dimensions should I make my garden in order to maximize the area? And so I just wanted to read through the question and make sure that's what it answered or asked. And so what I would say is that if we looked at our original one, we had w was 6. But remember that my garden looked like this, where I had w and I had h. So I also need to find h. So now I had to erase that, but originally in our work we had said h is 24 minus 2w. So if w is 6, h is 24 minus 2 times 6. 24 minus 12 is 12. So h is 12. So now the dimensions means both of those. So I should make my garden 6 feet by 12 feet. Or 6 feet by 12 feet. And so the final answer is, okay, the garden should be 6 feet by 12 feet, and that will maximize the area. It didn't ask for the maximum area. If it had, I should put it in there, but I've answered what it's given me, so that's exactly what I'm looking for. You guys have questions in there? Anything you want to go back over on there? Or anything else you want to see in there? I'll give you a second to answer while I look at whatever is going to be next. All right, number 17 was actually next on the list, Lonely Warrior. So that's perfect. So I'm going back through the comments and just looking at the order you guys gave them to me in. And so, let's see. Let's do number 17. We have f of x is x times x minus 2 cubed. I want to determine the intervals of increasing, decreasing, critical points, and local extrema, and then concavity and graph the function. So let's look at f of x equals x times x minus 2 cubed. All right. So the first thing we need to do is, well, if we want to find intervals of increasing, decreasing, and concavity, we first need to find the derivative. So if I look at this, what is the derivative going to be? Well, the big picture thing that's going on here is I have a product, so I have to use a product rule. So I'm going to get second d first plus first d second. My first function is x. My second is x minus 2 cubed. The derivative of the first is just 1. And now for the derivative of the second, it gets a little bit more complicated. So I would go off to the side and say, what is the derivative of x minus 2 cubed? Now as I look at that one, notice that I have a composition of functions. I have an inside and the outside, so I have to use a chain rule. So this is going to be the derivative of the outside times the derivative of the inside, where my inside function is x minus 2, and my outside function is I cubed. So the derivative of I cubed is 3i squared, and the derivative of x minus 2 is 1. So if I put these together, I get the derivative of the outside is 3i squared times 1. And remember, the last thing we need to do for the chain rule is to plug I in. So we're going to get 3 times x minus 2 squared. And so that's going to be the derivative of x minus 2 cubed. Now that we've finished this problem, we can go back to our original problem, which we needed this derivative because it was the derivative of the second. So if I put that together, I get x minus 2 cubed times the derivative of the first is 1, plus the first times the derivative of the second is 3 times x minus 2 squared. Sorry, the x minus 2 is squared. And so I'm left with this as my derivative. All right. Now, if I was just asking for a derivative, that'd be a great answer. But because you're going to need to find where this is 0 and undefined, it is helpful to simplify this here. And so now in simplifying it here, we can get a couple things going on, and this isn't the easiest thing to simplify. But what I'm going to notice is that I can factor some things out of this. What can I factor out is the x minus 2 is here, and x minus 2 is here. And actually we have x minus 2 squared in both of these terms. So I can factor out x minus 2 squared. And what's left over is I would still have 1x minus 2 left in this term. And in this term, the x minus 2 squared is gone, so I just have my 3x left over. So now what I get is x minus 2 squared times 4x minus 2. All right. I wanted to do that and to show you that's what happens here. We use the product rule, we get out this function, and then we can factor out the term x minus 2 squared, and we get this thing. Notice that we told you that when you're taking derivatives on the test, you're not going to have to simplify, so you won't have to do this process if you're just taking derivatives. And also, when we have this type of problem, that is, we give you a function and ask you to find the intervals of increasing, decreasing, and concavity, because you've already found derivatives, we'll actually give you the derivative here. So on the final, we're going to have, okay, if this is x, then f prime is, and then we'll actually give you this in the simplified form, so that you won't necessarily have to go through this whole process here on the final exam. because this is more algebra stuff that we're not trying to get at on the final. Does that make sense to everybody? Alright, so if this is where you're getting lost, you don't need to worry as much about it. Like I said, I did want to go through it and show you what's going on as we're just factoring out. But this isn't the part that, this wouldn't actually show up on the test. It would be, here's the function, and then here's the derivative. And then from there, you're going to have to go ahead and find the intervals of increasing and decreasing. So is that just for the long problems? Yes, just for the long problems, we'll give them to you. But remember, if I just ask for the derivative of this, you don't need to simplify it all. That's part of the test. So on these shorter ones, it would say find the derivative of this, which is a very possible question, but this answer would be sufficient. You wouldn't need to go through this part. And yes, the second derivative would be given as well for the concavity and inflection points. So it would give you, here's the function, here's the first derivative, and then it would give you the second derivative, and you'd have to find those things. So if this is the part that's scaring you, then don't worry so much about it, because that won't be part of the test. This was just, as I was going through, I wrote up the exam so that you could get a little practice with some of the arithmetic. But on the actual test, you won't have to do this. So, like I said, don't freak out about this portion, but you should be able to do the next portions correctly. So if we have this, how do we then find the intervals of increasing and decreasing? So let's actually go through that. So if my derivative is x minus 2 squared, that's 4x minus 2. And I want to find intervals of increasing and decreasing. I have to find where is the 0 and where is this undefined. So now if I look at this, notice that f prime is never undefined. And very good. And so where is it 0? Sorry, this is never undefined because it's a polynomial. Where is it 0? Well, this is 0 if x minus 2 squared times 4x minus 2 is 0. But now our product is 0 if one of the terms is 0. So what I get is x minus 2 squared is 0, or 4x minus 2 is 0. So if I solve these respectively, I would take the square root and get x minus 2 is 0. I'd add 2 and get x is 2. And on this side, I would get 4x is 2. So x is 1/2, or 2/4 if you prefer. Either way is fine. And so what I get is my derivative is never undefined, and it's 0 at 2 and 1/2. Now that I have that, I want to make a number line. So I'm going to make a number line for f prime. On there, I'm going to put the 1/2 I had. I'm going to put the 2 I had. And now I need to determine positives and negatives for each of these intervals. So therefore, all I'm going to do is pick something less than 1/2. So something less than 1/2 is 0. So I'm going to plug 0 in. Now we're trying to find the derivative, so I'm going to plug it into the derivative function. So I get 0 minus 2 is negative 2 squared is 4, which is positive. 0 minus 2 is negative. So a positive times a negative is just negative. If I pick something between 1/2 and 2, I would pick 1. 1 minus 2 is negative 1 squared is positive. 4 minus 2 is positive. So this ends up being positive. And then if I pick 3, 3 minus 2 is 1. 1 squared is 1 is positive. 12 minus 2 is 10, which is positive. So I also get positive over here. Therefore, I have what I need to find increasing and decreasing. Well, this function is going to be increasing if my derivative is positive. So it is increasing on, and so I could say 1/2 to 2 and 2 to infinity. So I'm going to write that as 1/2 to infinity, but if you want to say 1/2 to 2, you need 2 to infinity, that's okay too. Now it's going to be decreasing on negative infinity to 1/2. So on this interval here, so that's where it's increasing and decreasing. Now, my critical points, I know the x values already are 1/2 and 2, but I still need to find the y values. So for a point, we need an x and a y value. So to find the y values, we're going to want to plug in up here. So if I take 1/2, and we get, remember these are the y values to the original function now. So I would get 1/2 times 1/2 minus 2 is -3/2 cubed. And so what I would get is 3 cubed is 27. So -27. 2 cubed is 8 times another 2 is 16. So I get my -27/16. And if I plug 2 in, well, I get 2 times 0 is just 0, so that one's easy. So those are my critical values. All right. So help me out here. Is this one a local min, max, or neither? So let's see. We're decreasing and then we're increasing. So we're going to have a local min. Very good, guys. So this is going to be a local min. Oops, sorry. I meant to point to that one. At 1/2, we have a local min of -27/16. Now at 2, 0, do I have a min, max, or neither? We have an increase and an increasing, therefore we end up with well, I think that means I don't have a min or a max. Very good. So I have neither. Now, I just want to make sure that I've answered all the questions. So if I go back over that one, it says intervals of increasing and decreasing. I've done that. It wanted me to find my critical points. So I've done that. And it wanted me to determine local extrema. So I've done that as well. So that answers all of the part 1 of number 17. All right. So now, what we want to do is basically the same process again, except for we want to do it for the second derivative if we want to find intervals of concavity. Now, like I said, they're going to give you those, so I'm actually just going to give you the second derivative is going to be I just have to look it up real quick because I don't have it memorized. But if we write that down, it's going to be 12 times x minus 12 times x minus 2. All right. So now to point out what I was saying last time is this would be the problem is you would move on to the second part and you'd say, oh, here's f double prime is 12x minus 12 times x minus 2. Now can I find the intervals of concavity? So we go through the same thing. We find where's the 0 and undefined, positive and negative. So we'll actually just go ahead and go through that. So this is undefined. Well, this is never undefined because this is just a polynomial. So it's defined everywhere. And at 0 if 12 times x minus 12 times x minus 2 is 0. So remember, a product is 0 if one of the terms is 0. So I get 12x minus 12 is 0, or x minus 2 is 0. So if I solve this one, I get x is 1, or x is 2. And so these are my potential inflection points. And so in order to determine what those are going to be, or determine if those are inflection points or where my intervals of concavity are, I'm going to do the same thing and make another line for f double prime. So I'm going to put on 1 and 2. So I want to find is my second derivative positive or negative. So I'm going to plug in 0 because that's going to be less than 1. So 0 minus 12 is negative. 0 minus 2 is negative, so I get a positive. And then between 1 and 2, say 1.5, I would get 18 minus 12 is positive. And 1.5 minus 2 is negative. So a positive and a negative is negative. And the last thing I need to plug in is say 3. 36 minus 12 is positive. 3 minus 2 is 1 is positive. So a positive times a positive is positive. So now I have the information I need to find intervals of concavity. So the function would be concave up on, well, it's concave up whenever the second derivative is positive. So that would be negative infinity to 1, union 2 to infinity. And then it's going to be concave down on, well, 1 to 2. So there's my intervals of concavity. And then to find my inflection points, well, in order to be inflection points, remember I actually have to change concavity. So if I look at this one, notice I go from a plus to a minus. So I do have an inflection point at 1. And because I go from a minus to a plus, I do have an inflection point at 2. But if it had gone from, say, plus to plus, then this would not be an inflection point. So make sure to check your line before saying whether or not they're inflection points. But because each of them changes, I know that I have one at x is 1 and one at x is 2. So now to find the point, I need the y values. So to find the point at 1, I'm going to plug in 1. So 1 times 1 minus 2 is negative 1 cubed. So 1 times negative 1 cubed is negative 1. And if I plug in 0, I'm sorry, if I plug in 2, I get 0. So my inflection points are 1, negative 1, and 2, 0. Any questions so far on increasing, decreasing our concavity? I'm going to set up the next problem, but if you guys have questions, make sure to write something in there. Alright, so the next one is graph the function. And so if I want to graph this, what I have to do is remember all the stuff that I found in the first two parts. So I'm summarizing that by giving myself these numbered lines. The f prime number line looked like this. The f double prime looked like this. And again, you would refer earlier in the problem to see this. And we noticed that we had critical points here and here, and inflection points here and here. So those are points that we're going to be interested in. So we're going to end up having to graph them. Therefore, what I'm going to do next is figure out the shape of the graph. So anywhere I have a partition number or a number on either of these lines, I'm going to put those up on my top line. So here I had 1/2, so that's going to show up there. On the second derivative I had 1, so that's going to show up. And then on both of these I had a 2, so that's going to be on my function number line. Now, for my function number line, I want a shape. And so what I have here is decreasing concave up. So what I need to think about is what decreasing concave up looks like. So I'm going to start with concave up. It looks like that. And then decreasing is going to be this side of it. So on this entire interval, my function is going to have this same shape. It's going to be concave up, decreasing. Now from 1/2 to 1, notice that I'm increasing concave up as well. So I'm still in this interval for concave up. I'm in this interval for increasing. So increasing concave up would look like, well again, here's concave up. So the right-hand side is increasing. So that's the shape of the graph. Now from 1 to 2, if I look down, I'm still increasing because I'm in this portion here. But now I'm concave down. So concave down increasing is going to look like that. So increasing would be that portion. And then I'm going to be increasing concave up. And so we already looked at that one, looked like that. So now we have the shape of our graph. The next thing we need to do is just then plot out these points. So here's 0, 1, 2. So I'm trying to look at my numbers here. I need to get from -27/16 to 0. So let's go from -3 to 0 to make those points I'm interested in. And at 1/2, I'm going to be -27/16. So that's -1 and 11/16, which is, so I don't have to be exact here, but I'm going to say somewhere around here. Between -1 and -2 seems to be a good value. So I'm going to plot that point in. Now I can also plot in the point 2, 0. And I can also plot in the point 1, -1. So now I have those points because they were critical values or inflection points. And so the last thing I need to do is play connect the dots with these shapes. So on this interval, we're going to look like this. So I just want to draw that shape in. From 1/2 to 1, I'm going to get this shape. So I'm still concave up, but I'm increasing. And then from 1 to 2, I'm concave down, increasing is going to look like that. And then from 2 to infinity, I'm going to be concave up, increasing. So I'm going to get that shape there. And that's what we're looking for. That's the graph of x times x minus 2 cubed. Notice that we really want to see these things. These critical points, the inflection points need to be written down. I need to see the curvature and the increasing and decreasing, because that's what we're testing you on. Notice that you can plug this in your calculator and get a graph out, but if you don't show these details, you're not going to get full credit. So I wouldn't suggest doing that right away. Suggest trying to do your best here and then maybe checking your work against the calculator. All right. So that finishes up that one. If you guys have questions in there, make sure to write them in there. Otherwise, I'm going to look back up at the comments and figure out what was asked next so that we can go over that one. All right. So that would go on the list there. I think 14 is next, because that was the next one I had asked. All right, people had asked, but yes, we'll get to 25 eventually. So number 14 is the implicit differentiation problem. And so what we want to do is find dy dx if y cubed plus x cubed is equal to x e to the y. So, as we're setting this one up, remember the goal here is to find dy dx. If it was just y equals something, we know how to do that, or at least we would have seen it in the earlier problems, is use your rules, your product rule, your quotient rule, your chain rule, all the other things we came up with, and you just take the derivative. However, what we have here is we can't just solve for y in terms of x, so we have to do this a little bit more creatively. And so when we have things like this, what we decided that we're going to do is we're just going to take the derivative of both sides with respect to x and see what happens. What we hope is that a dy dx will pop out so that we can then find it. Therefore, I'm just going to take the derivative of both sides with respect to x. And I'm going to start with the easy one here. The derivative of x cubed with respect to x is just, well, if I look at that over here, the derivative of x cubed with respect to x is just, the normal derivative of x cubed is just 3x squared. We can use a power rule there and we're done. Now, it gets a little trickier if we look at y cubed, because y is actually a function of x. So we don't know what y is. If we did know what y is, we could find the derivative, but then we wouldn't have to do this whole implicit differentiation thing. So what we have to think about this as is y is a function of x. So I'm going to explicitly write that as y is a function of x. Well, what that means is that I actually have a chain rule here. So the chain rule says the derivative of the outside times the derivative of the inside. So my outside function, or my inside function is y. My outside function is I cubed. So the derivative of I cubed is just 3i squared. And the derivative of y with respect to x, well, we don't know what that is, so the best we can do is dy dx. So what we get is, using the chain rule, the derivative of the outside times the derivative of the inside, we get 3i squared times the derivative of the inside is dy dx. And the last thing we have to do is plug in I, but I is just y, so I get 3y squared dy dx. Now, I wanted to point out that we noticed that if these letters weren't the same, this was just one letter here, that what we really ended up doing is finding the normal derivative. So the normal derivative of x cubed is 3x squared, so the normal derivative of y cubed is 3y squared. But then, because y is not equal to x, we have to multiply by the derivative of the inside. So what we get is a normal derivative of 3y squared times the dy dx. And so this is what we were hoping for, is remember we wanted dy dx to pop out. It has done so. So I get 3y squared dy dx is the derivative of this portion. Any questions so far on the implicit differentiation? Yep, y is the inside function because it is a function of x. Because y is now a function that's inside of the cubed. So that's why we're treating it like an inside function. Any other questions there? All right. So the next thing we need to do is find this. And notice, if it was just y's or just x's, we could use that same trick here. But because we have x's and y's, what we have to do is realize that, okay, well, there's more going on here, so I have to use some other rule to find a derivative. And what I have here is x times e to the y. So if I'm going to take the derivative of x e to the y, that's a product, so I'm going to use the product rule. Second d first plus first d second. My first function is x. My second is e to the y. And then I have to find my derivatives. So now, when I'm finding my derivatives, remember it's with respect to x. So the derivative of x with respect to x is just dx dx. These are the same letters, so it's just a normal derivative as one. On the other hand, I have to find the derivative with respect to x of e to the y. Notice here again that y is not equal to x, therefore y is a function of x, so therefore it is an inside function. So when we're taking the derivative of the outside is just the normal derivative, which in this case would be e to the y, but we have to multiply by the derivative of the inside as the dy dx. So again, using our chain rule here, we get the derivative of e to the y as e to the y dy dx. So now if I put that together, I get my second is e to the y, as the derivative of the first is 1, plus the first is x, times the derivative of the second is e to the y times dy dx. So now what we could do from here is we found the derivative, our dy dx popped out. If we wanted to, we could group the dy dx's, put everything on the other side, and divide out. But I'm not going to require you to do that on the final. If you have someone other than me, you might have to do that. But then you would move these to one side, this to the other, and I'm going to move that one up for you guys. If you guys want to do that, let me know. Otherwise, we can move on to the next one. Or if you want to try another one like this, let me know that too. All right, I think 25 is next. Yes, Caitlin, you can just leave it as is. You don't, for me anyway. Like I said, if you have a different professor, you want to do what they tell you. But for me, I want it just like that. I prefer it like that because I don't want to test you on your algebra skills. I just want to see that you can do the derivative. And so that's what I'm looking for. That's what I want to see. Does that make sense? All right, number 25. So what I want to do is find the area under f of x equals sine of x plus 2 on the interval 0 to pi. So under this, and I should say, and above the x-axis on the interval 0 to pi. So, yeah, well, in the last one, you don't have to make it dy dx is equal to something. Like I said, other professors might, but that's not what I'm testing you on, so I'm happy to just leave it as it was. Going to this one, though, maybe you guys can help me out. If I want to find the area under the curve above the x-axis, this is really just a different way of saying find something. What is that something I'm actually trying to find? The integral, very good. The definite integral, even better. Awesome, guys. So the point is that all this question is saying is, if I want to find the area under the curve and above the x-axis, find the definite integral. So find the integral from 0 to pi of sine of x plus 2 dx. So now if I want to do that, all I have to do according to the fundamental theorem is find an antiderivative. So I need to find a function whose derivative is equal to sine of x plus 2. And so I'm going to start with the sine. Can I think of a function whose derivative is sine? Well, I think it's cosine, because I know cosines and sines have this weird property, but if I take the derivative of cosine, the derivative of cosine is actually negative sine, so I'm off by a negative, so I need to remember that. Okay, well, the antiderivative of sine is actually going to be negative cosine, so that when I take the derivative of negative cosine, I get negative negative sine on positive sine of x. All right, very good. And then if I want to find an antiderivative of 2, well, that's just a constant. So if I take the derivative of 2x, that is my antiderivative. And so what I've done is I found one antiderivative of sine of x plus 2. Now, it's always good to make sure to check your work, take the derivative, make sure you do indeed get what you started off with, and in this case we do. So now I just need to evaluate from 0 to pi. So to find that, what that means is just plug in pi. So I get negative cosine of pi plus 2 times pi minus, and then I'm going to plug 0 in. So I get negative cosine of 0 plus 2 times 0. And so if I follow this through, I get negative cosine of pi is negative 1. Cosine of pi is negative 1. If you guys don't remember that, you will have your calculators on you, so feel free to use those. But we would get negative 1 plus 2 pi minus are coming from the equation. Then cosine of 0 is 1. So if I get rid of some of these negatives, I just end up with 1 plus 2 pi is 2 plus 2 pi. And so that's exactly what we're looking for here, is just, okay, well, the area under the curve is going to be 2 plus 2 pi, because that's the definite integral from 0 to pi of sine of x plus 2. And the whole point of this problem is to make it look complicated by giving you this weird wording. But you just have to realize that when they say find the area under the curve, I'm really just finding the definite integral. And if you can make that step, then it becomes just a definite integral problem, so it's not too hard. Any other questions on that one? All right. Well, nobody else is asking questions, so I think the next one we had up was 21. So we'll go through that one. And notice that one's a graphing one again. We had done a similar one with the x times x minus 2 cubed. But this one actually looks a little bit more like just the graphing part. but it's split up so that you don't have to find quite as much in different parts. You just do it all at once. And so on the test, it would actually ask for the parts and then ask you to graph. So if you kind of put 21 and, what was that, 17 or 14, I can't remember. 17 and 21 put together are basically like one problem on the test. But what we have here is f of x is equal to x squared minus 9 over x squared minus 2x minus 3. And then they tell you what the derivative and second derivative are, so we'll use those as we need them. But what I want to do is graph this and label all pertinent information. The one extra thing we have here is we have something that's going on with the original function that we have to pay attention to, such as on number 17, we had a polynomial, so the domain was all real numbers, and we didn't have to worry about asymptotes or anything like that. But in this case, because the domain is not all real numbers, we do have to worry about things like asymptotes. So the first thing we're going to start off with is what is the domain? And so the domain is going to be, well, anywhere we don't break this. And we're going to break this at the bottom of 0. So we're going to break this if x squared minus 2x minus 3 is equal to 0. So I'm going to solve this equation. And I think I can factor. This is x minus 3 times x plus 1. So I end up with x is equal to 3, or negative 1. So my domain is all x, except for negative 1 and 3. So as long as x is not negative 1 or 3, we're in the domain of this function. So when we're graphing, we have to make sure that we don't draw points here. All right. The other things we have to find are vertical asymptotes and horizontal asymptotes. So how do we find vertical asymptotes? Is, well, we know that those can occur when the bottom 0 because they're not in the domain. So we want to check, do I have a vertical asymptote at each of these points? And the way to do that is to find the limit. So I'm going to find the limit as x goes to negative 1 of f of x, and the limit as x goes to 3 of f of x. Now, remember that the first thing we would do when finding the limit is we plug in negative 1. So if I plug in negative 1, I get negative 1 squared is 1, minus 9 is negative 8, over 1 or plus 2 minus 3 is 3 minus 3 is 0, so we get negative 8 over 0. So as a limit, if we get negative 8 over 0, we know that the limit is going to be undefined, so this limit is undefined. So that means that we have a vertical asymptote at x equals negative 1. So if you end up with, yes, the bottom is 0, I get a number over 0, that means I have a vertical asymptote at the point. Now, if I look at 3 though, if I plug 3 in, I get 9 minus 9 is 0, and it's 0 over 0. Alright, now I got 0 over 0. What that means is I don't actually know what happens. If it was a number over 0, I know it's an asymptote, but since it's 0 over 0, I have to do more work. So what I'm going to do is I'm going to look at this and say, well, if I wanted to find the limit of this, I got 0 over 0, I have to simplify it. I just saw your question. Yes, the live stream will be on YouTube afterwards so that you can watch it as many times as you would like. Sorry, getting back to this problem. Since I get 0 over 0, I can either factor both of these and cancel out, but I'm actually just going to use L'Hopital's rule just to get more practice with L'Hopital's rule. So remember, that's the derivative of the top over the derivative of the bottom. So the derivative of the top would be 2x minus 0 all over the derivative of x squared is 2x minus 2 minus 0. And now I have a new limit, so I can plug in 3. If I plug in 3, I get 6 over 6 minus 2 is 4. And so I get 6/4, or if you prefer 3/2. Notice that that's a number, right? Because that's a number, that means that my limit exists. Therefore, because the limit exists, I do not have a vertical asymptote here. So instead what I'm going to have is a hole. So I will have a hole at x equals 3, and then I could even say at the point 3, comma 3/2, because the limit value is 3/2. So as x gets close to 3, y is going to get close to 3/2. Questions so far? All right. So I have the domain. I have a vertical asymptote, and I have a hole as well that I found. The other thing I would need to find is horizontal asymptotes. So how do I find horizontal asymptotes? Well, what I need to do to find horizontal asymptotes is I take the limit as x goes towards either infinity, or the limit as x goes towards negative infinity of my function. And so, as I'm finding this limit, I'm going to look to the highest power on top and the highest power on bottom, so I can simplify this, because remember, as x goes towards infinity, this is going to become negligible, this is going to become negligible, so I get the limit as x goes towards infinity of x squared over x squared, which in this case is just 1, and if I do it as x goes towards negative infinity, I get the same thing, x squared over x squared is just 1, so I have a horizontal asymptote at y equals 1. So because I get a number out, I have a asymptote. If I didn't get a number out, I would not have an asymptote. But again, the way I did that is, on the top, I look at the highest power of x with its coefficient, and on the bottom, the highest power of x with its coefficient. I simplify, and I determine what the limit's going to do. All right. So that's all the stuff I need for my function. I know that I have an asymptote at -1, I have a hole at 3/2, and I have a horizontal asymptote at y equals 1. So I'm going to try to write that up here so I don't lose it. Alright, now what we need to do is continue with this. And so again, if we look back to number 17, it actually walks you through this and says, okay, if I want to find the graph, I have to find intervals of increasing, decreasing, and where the critical points are. So what I'm going to need is the derivative function. And so we were kind enough to give it to you on this one, as we will be on the test. So I end up with -2 over x minus 3 over x plus 1 squared times x minus 3. So now to find critical points, remember we find where the derivative is 0 or undefined. So if I want to find where this is undefined, I'm going to set the bottom equal to 0. And if I set the bottom equal to 0, notice that I get x is -1, or x is 3. So at 3, this is 0. At -1, this is 0. So at those 2 points, my derivative is undefined. Now, to find where it's 0, I'm going to let the top be 0. And so if I solve that one, I get, well, I divide by -2. I get x minus 3 is 0, so x is 3. But notice that at 3, I actually have 0 over 0 is undefined. So I wouldn't technically have a 0 derivative here. But in the grand scheme of things, it's not that big of a deal, because either way, 3 is going to be a partition number for my derivative. So what that means is, I look at my derivative, I'm going to put on -1 and 3, and then I'm going to determine positives and negatives. So I want to put in something less than -1. So less than -1 is -2. So if I do that, I get -2 times -5 is a positive up top. -2 plus 1 is -1 squared is a positive. And then I get -2 minus 3 is a negative. So if I put this all together, I get a positive over positive negative is negative. If I continue, something between -1 and 3 is 0. So if I plug in 0, I get -2 times -3 is positive. This is 1 squared is positive, 0 minus 3 is negative. So this becomes negative as well. Alright. And then if I plug in something bigger than 3, I get 4, for example. Negative times 4 minus 3 is going to be a negative. 4 plus 1 squared is positive. 4 minus 1 is positive. And so I end up with a negative. And if I combine that all together, that means that f is decreasing on negative infinity to negative 1, union negative 1 to 3, union 3 to infinity. If you want to say it's decreasing everywhere, that's okay. It's just it is decreasing everywhere that it's defined for. Now, we would want to find any critical points, but notice that at negative 1, do we have a critical point? It's no, because it's not in the domain. At 3, do we have a critical point? No, because it's not in the domain. So we actually don't have any critical points for this function. We just know that it's decreasing everywhere. Questions so far? All right. So I'm going to draw that up here. And I'm going to move on to my second derivative. So if I look at my second derivative, it's going to be 4 times x minus 3 over x plus 1 something cubed times x minus 3. And so that's what they give me in the problem. So if using that, I want to determine where is this 0 or undefined. So notice it's undefined if the bottom's 0. So again, that's going to be at negative 1 and 3, which makes sense because the function is not defined, so the second derivative can't be defined. And then at 0, if the top is 0, but the top's only 0 at 3, but at 3 I have 0 over 0. So therefore my derivative is undefined at negative 1 and 3, and those are the points I need for my second derivative number line. And we're going to go through the same process, plug in something less than negative 1 between these two and then bigger. So if I plug in something less than negative 1, like 0, I get 4 times negative 3 is negative. 0 plus 1 cubed, oh sorry, why am I plugging 0? I should plug in negative 2. 4 times negative 2 minus 3 is negative 5 is negative. Negative 2 plus 1 is negative 1 cubed is negative. And negative 2 minus 3 is negative 5 is negative. So negative, negative, negative is negative. Between negative 1 and 3 would then be 0. So 4 times a negative is negative. This becomes positive. This is still negative, so negative over negative is positive. And then if I continue, I'm going to plug in 4. So I get positive, positive, positive is positive. So what I get is concave down on negative infinity to negative 1, and concave up on negative 1 to 3, union 3 to infinity. So where my second derivative is positive, I'm concave up. Where it's negative, I'm concave down. And so I'm going to write that over here as well. So I end up with that picture. All right, good. So the negative 2 is just something less than negative 1. Arbitrary. If you pick negative 3, negative 4, I know you said you figured it out. But just if anybody else is looking, when I was picking numbers here, it's just something less than negative 1. Something between negative 1 and 3 and something less or bigger than 3. Any arbitrary number will work. All right, now I'm ready to graph this. So to graph the original function, I just have to combine these things. So I have f prime, f double prime. So negative 1, 3 is minus, 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 plus, plus. And then I'm going to make my shape number line. So for f, I have a negative 1, so I'm going to put a negative 1 up here. I have a 3 on both of these, so I'm going to put it up there. And notice here that I am decreasing concave down. So concave down looks like that. Decreasing is this portion. So that's what we're going to look like on this interval. On this interval, I'm going to be decreasing concave up. So here's concave up. Here's decreasing, so I'm going to look like that. And again, this one's actually going to be the same, decreasing concave up. So I end up with that picture. Now if I put that together, here's 0, -1, 1, 2, 3. And then I need to plot these things in. So at -1, I'm going to have a vertical asymptote. So I'm going to draw that in. I'm going to have a hole at 3 3/2. 1, 2, 3. So 3 3/2 is right here. So to make that a hole, instead of putting a closed dot, I'm going to put an open dot to say, okay, at 3, my function's undefined, but I'm going to approach there, so I'm going to put in a dot. I have a horizontal asymptote at y equals 1, so I'm going to draw that in as well. And now I'm actually ready to finish my picture up. So on this interval, notice I don't have any points, but I have to approach these asymptotes, and they have to be this shape. So the only way we can get that is something that looks like this. And then on this interval, I'm going to be this shape, and I have to have this as a vertical asymptote. So I'm going to start up here and come down. And remember, I have to approach this point. Now I'm not going to touch it because there's an open hole there, but I'm going to approach it. And then if I continue from there, I'm going to have the same shape, so it's still going to be concave up, decreasing. But I'm going to have one as a horizontal asymptote. So if I try to make that smooth, it's going to look something like that. Here I'm concave up, decreasing with the hole at 3 3/2. And then here I'm concave down, decreasing, so that I have my horizontal asymptote at 1 and my vertical asymptote at -1. And so that's kind of set up how we would do it on the test, except for it would ask for find increasing, decreasing as parts of the steps. Then in the end, you find the total graph. Questions on that one at all? Do you guys want to do any more graphing, or is that enough? All right. So the next ones that are up are the related rates ones. So we'll go through those together as well. And again, if you have questions along the way, please just say something and I'll stop and answer it. So if we look at number 15, what we have is I'm on a boat and I'm fishing. I have a fish on the line, I'm reeling it in, and it's coming in at some rate of 15 feet per second. Right now there's 100 feet of line out. The fish is 10 feet below the tip of my pole, and I want to know how fast to reel my line in order to keep the line taut. So with related rates, just like the optimization problems, we need to read it. So I read it, and now I need to draw a picture. So my picture is I'm fishing, so here's my boat, here's me. I'll even put a smiley face on because I'm fishing and I'm happy. Here's my pole, and then there's a line coming out to a fish. All right, so there's my picture. I do want to point out that, okay, right now I know that there's 100 feet of line out. I know that the fish is swimming towards me, so I'm going to put a little arrow, point it towards me, and that's at 15 feet per second, so I'm going to write that down. And then I know that the height between the tip of the pole and the fish is going to be 10 feet, so I'm going to put that in there. And then, because I have this line anyway, I'm going to connect those 2 points, so I end up with that picture. 10 feet, 100, moving in at 15 feet per second. I think that's everything that's given to me. All right, so to make sure you guys are still watching, what do I do next? Very good. I assign variables. Thank you. I appreciate you responding. All right. So what I need to know is what's changing. If I look at the 10 feet, notice that the fish is swimming horizontally, the pole is staying in the same spot, so the 10 feet is going to stay constant. So I don't need a variable there. I am reeling the line in, so this 100 is going to change. So I need to call that something. So let's call that line length, or L. So the line length is currently 100 feet, but it is changing. Also, the distance between the fish and me is changing at a rate of 15 feet per second. So that's telling me this is changing, so I need something for that. So I'm going to call this F for the fish's distance. If you guys like to use different variables, you're more than welcome to, but L for line length and F for fish's distance, that seems to make sense to me. So that's what I'm going to go with. Now that I have variables, I have to find rates or derivatives. So I have an F, so I need a dF, be something. And I have an L, so I need a dL, be something. And now notice that what's given to me is this 15 feet per second. So that's telling me the fish's distance with respect to time. So that's telling me dF dt is 15. Now I need to be careful here is, I want to know is it a positive or negative 15? And the way I figured that out is F getting bigger or smaller? Well, the fish is getting closer to me, so F should get smaller. And because it's smaller, dF dt should be negative. Now, dL dt isn't given to me anywhere in here. It doesn't tell me, but that's actually what it was asking for. So I'm going to write that down as my question mark and say that's what I need to find. All right, so I have L, I have F, I have dF dt. I know I'm looking for dL dt. What do I need to find next? You guys help me out. Well, what I need to do is find a function. Thank you. So I need a function that relates L and F. So I know something about dF dt, I know something about dL dt, so I need a function relating them. So in this case, what's going on is I have a triangle, and I'm trying to find sine lengths of a triangle. And remember that this is going to be a right triangle because we have a horizontal and we have a vertical. So I think I'm going to use the Pythagorean Theorem here. And so if I use the Pythagorean Theorem, in general that's going to be a squared plus b squared is c squared. So I'll write that down. But then I'm going to say, in this case, what are my side lengths? Well, one side length is 10. And since that's never changing, I can just leave it as 10. The other side length is f. So I'm going to write that down as f. The last side length is currently 100, but because that's changing, I can't use 100. I have to use L. So I'm going to get 10 squared plus f squared is L squared using the Pythagorean Theorem. So I have my picture, I have my numbers, I have my variables, I have my rates, and I have an equation relating the rates. So now what I need to do is implicitly differentiate this with respect to time. So we went over the implicit differentiation problem. We're going to do the same thing here. We're going to find the derivative with respect to time of 10 squared plus f squared, and the derivative with respect to time of L squared. So now if I do that, notice the derivative of 10 squared is, well, that's a constant, so we just get 0. And if I take the derivative of f squared, if we remember back to that, we have y's and x's. Here now we have f's and t's, but it's the same thing. F is a function of time, so therefore when I'm looking at this, this is a chain rule because f is inside of the f squared function. So the derivative of the outside is 2 times the inside, or the normal derivative is 2f. But because they're not the same variable, I have to use the derivative of the inside as df dt. And if we do the same thing over here, we get 2L dL dt. So what we get is, using the Pythagorean Theorem, we implicitly differentiate and we get 2F dF dt is 2L dL dt. Alright, we're getting there. The next thing we need to do is, well, we need to plug in what we know right now in order to solve for what we're looking for. So I'm going to do that over here. What I would have is 2 times f. And so I need to know f right now. Do I know f right now? Well, it's not given to me, but it's also not what I'm looking for, so I'm going to have to find it. How do I find it? Well, I know that the Pythagorean Theorem still holds. And so what I get is 10 squared plus f squared is, right now, L is 100. So 10 squared plus f squared is 100 squared right now. So f squared is 100 squared minus 10 squared. So f is the square root of 100 squared minus 10 squared. So I'm actually just going to write that down as is 100 squared minus 10 squared. If you would like to plug that in your calculator and get a decimal, you're more than welcome to. Or if you want to leave it like that, you're more than welcome to. But as I continue through, I have 2. I now have f. df dt. df dt is negative 15. Is equal to 2. L is 100. And then dl dt is what we're looking for, so we're going to leave it as dl dt. So the last thing we would do is divide, and we get dl dt is equal to, well, this 2 times the square root of 100 squared minus 10 squared times negative 15 divided by 2 times 100 is going to be approximately negative 14.9. Now, I clearly didn't just do that. I knew that from before, but the idea is that you would plug this in your calculator. dl dt is negative 14.9. So now we've solved our model. The last thing to do is write a sentence. So remember that L was the line length. So the change in the line with respect to time is going to be negative 14.9. What are the units going to be? Well, L is in feet. Time is in seconds. So the line length is going to be changing at negative 14.9 feet per second. So if I put that together, it is, I need to reel in at 14.9 feet per second. So now by saying reeling in, it means it's getting smaller, line length's getting smaller at the 14.9 feet per second. And so that answers the question that I was originally given. Do you guys have questions on that one? All right. Well, if that's making sense, we have. The next one is going to be the other related rates one. And here I'm standing on the shore of a calm lake on a beautiful spring day. I cast out and my fishing line and lure hit the water and it causes a ripple. So what I'm going to have you guys do is I'm going to give you a second to look at that one on your own, and in the comments tell me, what should my picture look like? What shape should I draw? And then tell me, what are my variables? And then tell me anything else that I need to know about my picture so that we can just work through this together. So I'm going to give you a minute while I sit here. I will be right back. All right. While you guys are working, Teddy went to come and say hi. So hi, everybody. He's actually napping, but I wanted him to say hi, so. Hello. Alright, I'm going to go give him back to his mother. Alright, I'm back. So, sorry, running up and down the stairs made me winded. So, if we were looking at throwing my fishing line out, what I end up doing is I have to pay attention to what happens as my lure hits the water, because that's what I end up interested in. So, my lure hits the water, and then what's going to happen is I'm going to have ripples circling out. And so really I could just focus on one circle. So in this case, yes, Mario, my drawing will be a circle. Now, my variables will be area and time, and there's actually one more, is the radius. So I'm going to need to know something about the radius of the circle, which I'll call R. I need to know something about the area, which I'll call A. And so what I get is the area and the radius, and yes, I'll have time as well. So I'll say T is time. Now, if I fill in the information I have, what it's told me so far is that the area or the radius of the ripple is increasing at 3 inches per second. So that means my radius is going to be going out and getting bigger at 3 inches per second. So I'll write that down. And then it wants to know how fast is the area of the ripple growing when the radius is 24 inches. So currently the radius is 24 inches. And so now what we're going to go through is, while I have my variables, I have my picture, I have the numbers written in. So the next thing would be the rates. So I have R. So I'm going to need dr dt, and I'm going to need dA dt, because I have both of those variables, A and R. They're changing with respect to time. So now dr dt is given to us because the radius is changing at 3 inches per second. So I get 3. Is it a positive or negative? Well, it's going to be positive because the radius is getting bigger. Now, dA dt is the rate of change of area. Well, it's not given to us, but that's actually what we're looking for, so that's my question. So I have my variables, I have my rates. Next thing to do is find the function. So what function relates the radius and the area? Well, in this case, we have a circle. So the area of a circle is pi r squared. So in this case, area is just pi r squared. So now I have a function relating the two. Since I want to know dA dt, I'm now going to implicitly differentiate. So as I take the derivative of both sides with respect to time, so if I take the derivative of the left-hand side, well, I'm taking the derivative of A with respect to t as just dA dt. There's nothing more I can do with that. It just is dA dt. But here I can factor the pi out, so I'm going to do that because it's constant. And now the derivative of r squared, notice that r is not equal to t. So therefore, again, this is going to be a chain rule. The derivative of the outside is 2r. The derivative of the inside is the dr dt. So what I get is The normal derivative is 2r times dr dt. Now that I've implicitly differentiated, I just need to plug in what I know to find what I'm looking for. dA dt is what I'm looking for. I have pi times 2 times r is just 24 right now, and dr dt is 3. So I end up with dA dt is going to be equal to 48 times 3, which is 146 times pi. I don't know, I'm doing it in my head, so I hope I'm correct. Let's see. 8 times 3 is 24. 144 pi. There we go. I think I got it right that time. You guys should check my work, though. If we look at this, though, what that tells me is, yes, I have, okay, dA dt is 144 pi, but I still need to, or that is the answer to my model, but I still need to answer the original question. The original question was, at what rate is the area changing? So how are we going to answer that is, well, the unit should be area is in, since r is in inches, it's going to be in inches squared. Pi is unitless, so area is just inches squared. Time is in seconds, so this is going to be square inches per second. So if I write out my sentence, the area is getting bigger by 144 pi square inches per second. And so now we have a solution to the final answer. Now, for both of these, remember, the big thing is we need to be able to draw a picture. If you draw the wrong picture, then you'll end up missing some information, but try to do the best you can, draw out everything you have. Again, even if you don't get all of these, try to get as much credit as you can. Don't freak out on these, which happens a lot in the final. You see these and then people don't do anything. Do as much as you can, and little thing you do is going to give you extra points, so get as far as you can. But just make sure that you're saying, okay, what's going on here? After what's going on, can I find some variables? Can I find some rates? Can I find a function? Can I differentiate? Can I then solve for the answer? And so if you're doing each one of those steps, they're not that bad. It's just trying to put it all together that becomes cumbersome. So take your time with it and do every step you can. All right. Did you guys have any more questions on related rates? That's actually all the questions you guys have given me so far. So do you have any other problems you want to go over? Or is there anything else you would like me to talk about for the final? Yes, the grading will be the same as it has been for the other tests, so partial credit will still go through. So I'm grading it, that it'll be graded exactly the same as the other tests have been. The questions will be slightly different, but very similar. And so overall, basically just expect the normal test multiplied by 3. I don't know the exact answer to that question, Caitlin, but imagine a normal test times 3 is about the best I can give you. So our normal tests were like 6 or 7 questions, so 18 to 21. So let's call it approximately 20 is actually a pretty good approximation. Is that good enough? All right. Well, if you guys don't have any other questions, I'll end this early. But please, speak up if you guys want to go over anything else. Can we do 20? We sure can. Thank you for asking. Alright. Alright, so 19 and 20. 20 we actually did a little bit ago. So I'm actually going to let you look back over that one instead of going through it all again. But I might do it after 19. So I'm going to do 19. Number 3. So what we have is we want to find the limit as x goes to infinity of x times natural log of 1 plus 2 over x. Alright, so now as I'm looking at this, if I want to find the limit as x goes towards infinity of x natural log 1 plus 2 over x, the first thing I should do is basically plug this in and see what happens. If I do that, I'm going to get infinity times natural log 1 plus 2 over infinity is infinity times natural log of 1 plus, well, 2 over infinity is 0. So I end up with infinity times natural log of 1. Natural log of 1 is just 0. So I get infinity times 0. Therefore, we get an indeterminate form. We don't know what infinity times 0 is. So what we need to do is do some more work. Now we can't quite use L'Hopital's rule because we don't have a quotient. We need either infinity or 0 over 0. So what I need to do is take a product and turn it into a quotient. So the way I'm going to do that is instead of multiplying by one of these, I'm going to divide by 1. So I'm going to take natural log of 1 plus 2 over x. And then instead of multiplying by x, I'm going to divide by 1 over x. Because dividing by 1 over x would just be multiplying by x. So now I have a quotient. If I indeed plug infinity in here, I get natural log of 1 is 0. 1 over infinity is 0. So now I do have the 0 over 0 form that I need for L'Hopital's rule. Alright, so with that said, what I need to do is find the derivative of the top and the derivative of the bottom. So I'm going to start with the derivative of the bottom because it's a little bit easier. So if I find the derivative of 1 over x, that's going to be x to the negative 1. So that's going to be negative x to the negative 2. So the derivative of the bottom is negative x to the negative 2. Now for the top one, I have natural log of 1 plus 2 over x. And if I'm finding the derivative of that, notice what's going on, is that I do have a chain rule. So I have an outside and an inside, and I have to take the derivative of the outside times the derivative of the inside. My inside function is the 1 plus 2 over x, and my outside is natural log of the inside. Now, for the derivative of the inside, the derivative of 1 is 0, and this is 2 times 1 over x, so this, following the same reasoning as before, would just be negative 2x to the negative 2. However, what's the derivative of natural log of I? You guys help me out here. What's the derivative of natural log of I? All right. I don't know if I'm just waiting. All right. Well, the derivative of natural log of I is 1 over I, so we do need to know that. So we're going to get 1 over I. And so the derivative of the outside is 1 over I times the derivative of the inside is negative 2x to the negative 2. So I put that together, I get negative 2x to the negative 2 over I was 1 plus 2 over x. Thank you, Mario. Alright, so if I put this all together, what I get is negative 2x to the negative 2 over 1 plus 2 over x over negative x to the negative 2. Now, if I actually plug in infinity again, I'm going to get 0 over 0 all over again, and I could use L'Hopital's rule again. However, before doing so, I do want to simplify this. And so the way I'm going to do that is I get x to the negative infinity, and I would get negative 2x to the negative 2, 1 plus 2 over x. Since I'm dividing by this, I'm going to multiply by the reciprocal just to make things look a little nicer. And if I do that, what I notice are the negatives cancel, the x to the negatives 2's cancel, and so I'm left with the limit as x goes towards infinity of 2 over 1 plus 2 over x. Alright, now that I have this here, what I'm going to say is, well, let's plug in infinity again and see what happens. If we do that, we get 2 over 1 plus 2 over infinity. But 2 over infinity is 0, so 1 plus 0 is 1. 2 over 1 is 1. So I'm sorry, 2 over 1 is 2. So 2 is a number, so that's going to be my solution. So again, I'm going to use L'Hopital. I'm going to turn this into a quotient, use L'Hopital's rule, simplify, plug in, so that I can finally get out my final answer here. Questions on that one? All right. Speak up if you do. Otherwise, I'm going to go back to number 20, since nobody else has asked any questions. But I'm going to change it a little bit. Not a lot, but a little bit. All right. So if we looked at number 20, remember what happened was I wanted to make a garden in my backyard. We ended up drawing a box. And so we had, here's my backyard. Here's my garden. Now, what I'm going to do differently this time is last time we had 24 feet of fencing, but what I want to do this time is I want to make it so that I have 100 square feet of area, and I want to minimize the amount of fencing. So, thank you. I'll get to 24 next then. I do want to do this one a little bit differently, just to help out and give you another optimization problem. So the distinction is I still have the same garden, but this time I want 100 square feet of fencing, or 100 square feet of garden. If I want to minimize my fencing, I want to know what are the dimensions and how much fencing do I need. All right. So now the way we're going to do this is similar to last time. Is we have to figure out what's variable. And so we had the width and the height was variable. And now because we want to maximize our fencing, we actually have to determine the amount of fencing, or F, as a function of H and W. And now what that's going to be is the amount of fencing was W and a W and an H. So I actually want to minimize 2W plus H for this given equation. Is that making sense so far? Now, remember, again, we want to minimize this, and where the minimums are going to occur is at the critical points, so we have to find critical points. So we're going to have to find the derivative of this. The problem with this is it has two variables, so I have to get rid of one variable in terms of the other. How am I going to do that here is I have to use what's given to me. Last time I was given the amount of fencing, but this time I'm given the amount of area. So what I know is that the area is 100, but the area is also equal to, well, in terms of my variables, it's H times W. So what I get is 100 is H times W. Now, I'm going to solve for h in terms of w, so I'm going to divide by w, and I get 100 over w is h. So I can use that to say the amount of fencing is 2w plus 100 over w. And so what I want to do is I want to minimize this function, 2w plus 100 over w. All right. Now I also need to know the domain of this so that I know my answer makes sense. So if I'm looking at this, remember last time we decided that w is a length and h is a length, so both have to be non-negative. But now in this case, can w be 0? If w is 0, I'm going to end up with something like that. So if w is 0, notice I can't have any area, so I can't have 100 square feet of area. So actually what I have to have in this case is w has to be strictly greater than 0. On the other hand, I can actually let w get as big as I want, because I can keep letting h get smaller to keep my area at 100. So the domain for this one is just w is greater than 0. Now this is actually why I decided to do this one, is this is no longer a closed bounded interval with a continuous function, so we don't necessarily have a max or min. So what we actually have to do is go through this and see what happens to determine if we can actually find a minimum amount of area, or if that's just not going to happen. Now, what we can get here is we'll go through the process, and we want to find critical points, so now I need to find the derivative. The derivative of 2w is 2, plus 100 times the derivative of 1 over w is the same as the derivative of w to the negative 1. So that's 2 minus 100 w to the negative 2. So that's 2 minus 100 over w squared. All right. So if I want to find critical points, I have to find where is this undefined. Notice that this is undefined at w equals 0, because then I would be dividing by 0. However, that's not a critical point, because w equals 0 is not in the domain, so this is not a critical point. On the other hand, I have to have if 0 is equal to f prime, then 0 is equal to 2 minus 100 over w squared. So if I add that over 100 over w squared is 2. 100 is 2w squared. 50 is w squared. So w is the square root of 50. Now you could take the plus or minus, but because we're only worried about positive w's, we'd have to have this positive square root of 50. So therefore, the square root of 50 is the only critical value for this function. Now, just to remind you, if we have only one critical value, what we know is that if it is a local minimum, it's an absolute minimum. And if it's a local maximum, it's an absolute maximum. So what happened here was, even though we don't know we have to have a max and min, we ended up with exactly one critical point. Because we have exactly one critical point, if we can show it's a local extrema, it has to be a global extrema. So now what's left to do is to show that this is actually a local minimum. Because again, we're hoping to minimize, so we're hoping this is a local minimum. How would we do that? Well, what we did when we were dealing with extrema was we made a number line for the derivative. So I'm going to do that here. I'm going to find the derivative of fencing. Is the domain starts at 0. I'm going to have the square root of 50 here. And then I have to determine on each side, is my derivative positive or negative. So if I pick something less than the square root of 50, like 1, I plug 1 into the derivative function. I get 2 minus 100 over 1 is going to be negative. And if I plug in something bigger than the square root of 50, like 100, I will get 2 minus 100 over 100 squared is 2 minus 1 over 100 is positive. So what we end up with is a decreasing then increasing function. So what happens at the square root of 50 is we have a local min. Therefore, since it's the only critical value, it is a global min, so we have an absolute min at w equals the square root of 50. Now, remember that what I wanted to do is find the dimensions that minimize the amount of fencing and the amount of fencing. So I haven't quite found the dimensions. I found W, but I still need to find H. So to find H, remember that we had solved for 100 is H times W. So H is 100 over W. So H is going to be 100 over the square root of 50. So to answer my original question is the dimensions that would minimize the amount of fencing is square root of 50 feet by 100 over the square root of 50 feet with the total fencing being, well, I'm going to have two W's, so 2 square roots of 50, plus one of these is 100 over the square root of 50 feet. And the units will be in feet, because my area is in square feet. Now, the only thing I want to point out here is that I'm using square root of 50 and 100 over square root of 50 just because I don't have a calculator with me and it's easier to write those down. But you're welcome to use a calculator, get those out as decimals and write those in so that you have your answer there. Does that help out with the optimization? Do you guys want to do another one of those? Questions at all on that one before moving on? All right then. The next one I see is number 24. So we'll move on to number 24. So we have the integral from 0 to 1 of x cubed times x to the 4th plus 2 cubed dx. So what I want to find here is the definite integral. But what we know is that if we can find an antiderivative, we can evaluate from 0 to 1 and get the definite integral. So before I answer this question, I actually want to find what is the general antiderivative of x cubed times x to the 4th plus 2 cubed. So help me out here, guys. Do you know what the answer is going to be? If you do, write in the answer. If not, just write a no. I'm going to wait for some response, though. No. Thank you. I appreciate that. I'm used to asking questions and not getting any answer. So the thing is here is that because there's a delay, I don't know if you're not answering or if you're just ignoring me. So it's a little bit different than usual. Anyway, we'll be back. So no, the answer is Anthony. And then Mario says substitution. And Caitlin says no. So that's exactly right. So we do not know the answer directly. So what we want to do is try our other technique of integration, which is substitution. Our first one is guess. Our second one is use substitution. So the substitution here is, well, the inside function is going to be x to the 4th plus 2. So now, if that's I, what we're going to get is that di dx is going to be, well, the derivative of I with respect to x is 4x cubed plus 0. And so what we wanted to take from this is that then di is 4x cubed times dx. So it's di is the derivative times dx. So di is 4x cubed dx. Now, the next thing I want to say is I'm going to solve for dx. So dx is going to be di over 4x cubed. And so now I'm going through this process. Here's I, here's di, here's dx. Next, I can actually substitute in. So now the x cubed I'm going to leave alone. And then instead of x to the 4th plus 2, I'm going to put I, and that becomes cubed. Instead of dx, I'm going to put in di over 4x cubed. So all I'm doing is I'm substituting in I, and I'm substituting in dx in terms of di, and I'm left with the new function. The goal here is to make a simpler function, but we have to make sure we get rid of all the x's first. So now I'm going to look at this. Notice that I have x cubed over x cubed, so the x cubes do cancel. To help myself out, I have a 4 on the bottom, so I'm going to pull that out as a 1/4 times the integral of I cubed di. So notice that I've taken this complicated integral and I've turned it into a simpler integral. Instead of working in x's, I'm working in i's, and I end up with, oh, I just need to integrate I cubed di. Well, that one we can guess, because we can just use a power rule. So we get 1/4 times, add 1 to the exponent, divide by the exponent, plus my constant of integration. So the integral of I cubed is I to the 4th over 4. So I've completed this integral. It is now just I to the 4th over 4. The last thing I need to do is plug in I. So I get 1/4 times x to the 4th plus 2 cubed over 4, to the 4th here. So I to the 4th over 4 times 1/4 plus c. So my antiderivative is going to be 1/4 times x to the 4th plus 2 to the 4th all over 4 plus c. All right. Now that we've completed that part, what we want to do is we want to use that to find the definite integral from 0 to 1. So to do that, all I need is one antiderivative. So if I pick one of these, I'm going to get 1/4 times x to the 4th plus 2 to the 4th over 4. Now the point here is because I need 1, I don't need the plus c. I can leave that off. So I'm going to choose this one. And then I'm going to evaluate from 0 to 1. So what does that mean? Well, that means plug in 1 and then subtract off plugging in 0. So I get 1/4 times 1 to the 4th plus 2 to the 4th over 4 minus 1/4 times 0 to the 4th plus 2 to the 4th over 4. And so if I put that together, I get 1 plus 2 is 3. 3 to the 4th is 3, 9, 27, 81 over 16 minus, and then 2 to the 4th is 16 over 16. And if I finish that off, I just get 65 over 16, or 4 1/16 if you prefer. So when we're stuck with this, remember, I don't know the answer right away. That's fine. I'm going to use substitution. That's the only technique we have. The inside function I write down, then the di, then the dx, I substitute in, then I integrate, and then I plug my x's back in to find an antiderivative. Come back up to the top. I evaluate from the lower bound to the upper bound by plugging those in, and finally I get the area under the curve. Questions on that one at all? Or did you want to do a similar one? Let's just try a similar one. Let's try, I don't know, the integral of x cosine of x squared plus 1. Well, just to give you a little bit more practice with these, I want to integrate this. I'm just going to do indefinite integral. But if I look at this, I want to say, can I find the antiderivative? If I can guess it, great, but I'm going to assume no. So what I'm going to need is a substitution. So I need an inside function. So what's my inside function going to be? You guys help me out here. That is exactly right. Thank you. So the inside function is the x squared plus 1. So because that's my inside function, I now need to find di. And remember, di is the derivative. So the derivative of x squared is 2x. And then I multiply by dx. So di dx is 2x. So di is 2x dx. If I solve for dx, it's going to be di over 2x. And what I end up with is the integral of x. I'm going to leave alone. Cosine of I di over 2x. So again, the x wasn't part of the I or the dx. I left it alone. The cosine stays the same. The inside I put in I, and instead of dx, I get the di over 2x. What I end up with then is the x's cancel, and I'm going to have this 2. So I'm going to pull it out as a 1/2. So I get the integral of cosine of I di. So now I need a function whose derivative is cosine. So I'm going to get a sine here. So I found the antiderivative sine of I. I should check this to make sure the derivative sine is positive cosine. I always check because the negatives get weird with sines and cosines, but the derivative sine is positive cosine, so the antiderivative is 1/2 sine of I plus c. And the last thing I need to do is plug in I. So now that I'm done integrating, I can plug in my x squared plus 1. So what I end up with is the antiderivative of x cosine of x squared plus 1 is 1/2 sine of x squared plus 1 plus my constant of integration, c. All right. Any other questions then? Even if we've already done it, feel free to ask questions. If you want to do a related one to one of the previous problems, I will try to come up with something reasonable on the fly. But just let me know what you're thinking. All right, well, nobody's speaking up. So I'm going to go with, we'll just call it there. We've been at it for a while now. If you guys need to review more, you can. This is going to stay up on YouTube, so you're welcome to watch this over again. Or if you have dire questions, feel free to email me too. I'm happy to answer those. Otherwise, best of luck to you guys. Good luck studying. I hope it all goes well, and I hope the test goes well. So I'll either see you tomorrow or Friday, depending on what class you are. And thank you guys for joining me. It was great to have you.